It's 9:30 and time to start. Many people are still in bed, but that's their problem. So we will start today again with a talk on epidemics, this time by Frank Ball, who will speak about epidemics on networks.
Okay, thank you very much, Mia, and thank you for the organisers for organising this workshop and giving me the opportunity to speak in it. So this talk's going to be in two parts, and it's going to describe two extensions of the standard epidemic, SIR epidemic, on a configuration model network. The first part's based on joint work with Peter Neal, who's at the University of Lancaster, and we're going to add casual contacts to the model. I'll explain what that is shortly. And the second part is based on joint work with Tom Britton and David Searle, and we're going to add sort of clustering to the network. Okay, so sort of classically, a long time ago, epidemic models usually assumed a homogeneously mixing population of homogeneous individuals. So all individuals behaved, if it's a stochastic model, according to the same probabilistic law. Of course, that's not very realistic because it's important to include, in human populations, for example, there's individual heterogeneity, and there's also sort of social structure, which can have significant impact on how disease spreads, and it's important to try and include that in the models so that they better reflect reality. And there's been, in the last, 20 or 30 years, there's been a lot of interest in so-called structured population models, which sort of incorporate realistic departures from homogeneous mixing whilst trying to maintain some level of mathematical tractability. Okay, it's quite easy to write down quite a realistic model for how an epidemic spreads, but then you can do no mathematics with it. So what we try to do is to incorporate sort of departures from homogeneous mixing where you can actually still do some mathematics and not just have to resort to sort of simulation models. And one class of structured population models is those involving random networks. As I said earlier, in this talk I'm going to give two extensions of the standard SIR epidemic on a configuration model network. Okay, so the basic idea of these sort of network epidemic models is you have some sort of random network of say friendships, and you can only spread the disease to neighbours in the network. So you have a random graph, and it's often a configuration model random graph of sort of friendships, and then you spread an epidemic on that random graph. And okay, in real life epidemics, you're very likely to spread the disease to your friends, but it's also quite likely that you'll meet people who aren't your friends, say on the train or at the shop or whatever, and be able to pass on the disease to them. So what we going to include is the possibility of sort of random homogeneously mixing contacts superimposed on the network. So that's one model I'll be describing. And the second model I'll talk about, I think Tom mentioned yesterday, the configuration model. If n's large, you don't see any sort of triangles. It's sort of locally tree-like, whilst real human populations are not like that at all. And so I'm going to describe one way of modifying the configuration model so that we can introduce both clustering and degree correlation in a way that it can be tuned. Okay, so I don't really need to go through this, just to set the notation. So D is going to denote a typical degree of a typical individual. Mu D would be the mean of a degree distribution. And so we form a network by the configuration model. So you take capital N IID copies of this degree random variable. Sn is the sum of the degrees. If Sn is odd, you can just repeat it until it's even. And then you pair up, then you attach Di half edges or stubs to each individual I. Then you just pair these all up uniformly at random, and that gives you a network. There may be some imperfections in the network, so there may be sort of individuals who are connected to themselves, or there may be parallel edges between individuals. But if the variance of this degree distribution is finite, then they become sparse in the network as n goes to infinity. Okay, the epidemic model we're going to have, it's going to be an SIR epidemic model. So I think Tom explained this yesterday. So somebody starts off being susceptible to the disease. If they have contact with an infectious individual, they become infective. In this model, they'll become infectious immediately and be able to spread the disease to other individuals. They will have finite infectious periods. So I1, if individual 1 becomes infectious, they'll have an infectious period of length I1, which is their RID according to this random variable I. And after their infectious period is finished, they'll be removed and play no further part in the epidemic. They'll be immune to further infection. All I'm going to talk about will be concerned with the final outcome of the epidemic, what happens when the epidemic is over. And as far as the final outcome is concerned, you can add a latent period, it doesn't change the distribution of the final outcome. So I could describe an SEIR model, and all the results I will describe also hold equally well for an SEIR model. Okay, whilst infectious, individuals are going to make two types of contacts. They're going to make local contacts along each, so the individual I has got DI neighbours. They'll make local contacts along each of those to each of those neighbours independently at rate lambda L, and they'll make global contacts of individuals chosen uniformly at random from the whole population at rate lambda G. And these are of course governed by Poisson processes. So I'll call the formal local contacts, and these casual contacts I'll sometimes be calling them global contacts. So two special cases: if I set lambda L equals to 0, there's no spread in the network, I just recover a standard homogeneously mixing epidemic model. If I set lambda G equals 0, there's no casual contacts, and we just recover the standard network model. Okay, so here's some simulations of the final outcome of that model. So on the top row, the population is a size 250, and the bottom row, it's a size 1,000. There's this parameter R0 is a basic reproduction number. I'll explain how we can derive it for this model, but it's what Tom described yesterday. It's a threshold parameter which controls whether or not a major outbreak is possible. So if R0 is larger than 1, there's a possibility of seeing a major outbreak in a large population. If it's less than or equal to 1, you won't see a large outbreak in the limit. So here, this first population, the first two, there's no global contacts. This one's below threshold because R0 is less than 1. This one's above threshold, and now I've just added some global contacts in as well. And if R0 is less than 1, then you only see minor epidemics. The distribution looks roughly like this. If R0 is larger than 1, then you get a bimodal distribution. You may see it's quite a high probability often of seeing a minor epidemic, but it may take off and spread to a significant portion of the population. And the cutoff between major and minor outbreaks is not always clear, but as you increase the population size n, it then becomes quite distinct. And you can see here, when you add in these extra global contacts, then it sort of moves the mass of this large outbreak. Well, it increases the probability you get a large outbreak, and it moves it out closer to the maximum population size. Okay, there's a whole load of questions you can ask about these sorts of models, but some of the key questions are, well, can an epidemic started with few initial infectives become established and lead to a major outbreak? As I've already mentioned, the basic reproduction number, which is going to be a threshold parameter which sort of answers that question. And if that parameter is larger than 1, then you might want to work out the probability that you see a large outbreak. If so, how large will this outbreak be? So you like to develop some sort of law of large numbers. So if we go back to this picture here, so you have these large outbreaks. You like to work out what is the asymptotic mean of a large outbreak, and also to get a associated central limit field. And there's a host of other questions. These are the sorts of questions I'm going to answer. Of course, there's other questions we might well be interested in. We might be interested, I think in Tom's talk yesterday, he mentioned a bit how fast the epidemic takes off if you do see a large outbreak. The initial asymptotic will take off exponentially initially until you get saturation of susceptibles, and you may be interested in how fast it takes off. And to be precise, I'll describe a major outbreak as one which infects at least log n individuals. I never used to be very precise here, and then somebody asked, what do you mean by a large outbreak? And I said at least log n, because all the theorems are easy to, well, not easy, but are clear to state if it's at least log n. And then they said, well, that's not very large. But in fact, the theorems are also easy, well, could also be proved fairly equally easily if you make n to be n to the alpha, where alpha is less than a half. And if you go back to these pictures, in fact, what happens if you have a large outbreak and n is large, its size is of order n, but the cutoff, how big it is, depends on the parameter values, and the cutoff could be very small fraction. So I would just use log n for a large outbreak, but essentially the thing just splits into two. Okay, well, to get a basic reproduction number, we suppose that n is large and there are few initial infectives, and then the early stages of the epidemic can be approximated by a two-type branching process. So there's be two types of individuals in this branching process. The type L infectives would be those infected locally, i.e. through the network, and type G infectives will be those which are infected globally, i.e. by a global contact. And at the early on in the epidemic, if you think about global contacts, they're being picked with people chosen uniformly at random from the whole population. So early on, you're very unlikely to contact somebody who's previously been contacted. So every infectious contact becomes a new infective. And similarly for the local contacts, if you think about the way the configuration model of the network is formed, because you're sort of picking, all these stubs are sort of paired up uniformly at random, again, when you make your local contacts early on in the epidemic, you're unlikely to pick somebody who's already been infected, and so you can approximate it by a branching process. And you can use a coupling argument to make this fully rigorous. So the mean offspring matrix of this branching process, well, it's a 2x2 matrix. If you think about these elements, this element here, so if you've got a global, somebody who's contacted globally, okay, they make global contacts at rate lambda g through an infectious period which has mean mu I, so the average number of global contacts they make is lambda g times mu I. And the same would be true for somebody who's contacted from locally through the network as far as their global contacts are concerned. Somebody who's contacted globally in the network, they just picked an average random from the population, so their degree would be distributed as according to the degree distribution, random variable capital D. So they'll have on average mu D neighbours, and they contact them each at rate at probability PL. Okay, so they've got to make this plus on contact before their infectious period ends. So PL is given by that expression over here. While somebody who's contacted locally through the network, they'll have this size bias degree distribution, as Tom explained yesterday, because somebody who with degree k is sort of k times as likely to be contacted as somebody with degree 1 when the network is formed. But one of their nodes has already been, one of their sort of links has already been used up to become by the person who infected them. So there'd be, if I call d tilde the size bias degree distribution, then there'd be mu d tilde minus 1, the mean number of neighbours of that individual. And so the mean number of local contacts made by somebody who was contacted locally through the network is given by this expression here. Then R naught is just the maximum eigenvalue of that 2x2 matrix. I mean, you can write an expression. I think may have wrote an expression down for it yesterday, but it's with some quadratic. And in the limit as the population size goes to infinity, the probability of a major outbreak is strictly positive if and only if R0 is larger than 1, and I'm not going to do it, but you can work out the extinction probability of this two-type partial process, and that gives you the probability that you see a large outbreak. Okay, so that sort of explains what happens at the start of the epidemic. I now want to think about, suppose you have a large outbreak, I now want to explain how you can calculate the distribution of that large outbreak. So to do that, I'm going to introduce the concept what we call susceptibility sets. So what we do first of all, we form a directed graph of what I call potential local contacts. So these are all the individuals in the population. So for each individual, you could sample from their infectious period, you can sample from all these +1 processes, and you could write a list for each individual. If they have become infected, who they would then infect in the epidemic. And if one individual infects another, you draw a directed arc from the first individual to the second. So you can form this sort of random directed graph, which is a possible example. Okay, and now, to focus on some individual I can ask the question, well, if this I want the set of individuals that if they were to become infected, in this case it's going to be by a global contact, would lead to the infection of I by a chain of local contacts. So I look at the set of individuals, and here it's the blue set of blue individuals that are connected to I. There'd be a chain of directed arcs from each blue individual to I. And anybody not in this blue set, there's no chain. From this guy here, for example, there's no chain of arcs that leads to this individual I. And the susceptibility set is going to consist of all those blue individuals plus the individual I itself. Okay, and in our epidemic model with global contacts, this individual I will be ultimately infected by the epidemic if and only if one of the members of its susceptibility set is contacted globally by somebody during the course of the epidemic, or one of the members of its susceptibility set is the initial infective. Okay, so first of all I'll give a heuristic argument, and then I'll explain, not giving much detail, how we can make this heuristic argument fully rigorous. So let's suppose the population size n is large and there's few initial infectives, and suppose there's a large outbreak, and let Z be the expected proportions of the population that are infected by this large outbreak. And let pi be the probability that a typical susceptible avoids infection, a global infection, during the course of the outbreak of the epidemic. Well, if fractions Z are infected, then there's NZ individuals infected during the course of the outbreak. They each infected on average for length mu I. So this, on average, is this amount of infection out there in the population, which is trying to infect our individual globally at rate lambda g upon n. All these things happen at points of +1 processes. So the probability this individual avoids global infection will be just given by e to the minus lambda g z times mu I. Now 1 minus z, z is the fraction infected, or expected fraction infected, so 1 minus z is the probability a typical susceptible avoids global infection, during the course of the epidemic. And that individual will avoid infection if its local susceptibility set avoids being contacted globally. And those individuals in that local susceptibility set, when n is large, they're being contacted globally almost independently, close to independently, and so the probability it's susceptible avoids infection by the epidemic will be given by this, well, you just sum over the distribution of the size of this local susceptibility set. This is sort of limiting, so I'll explain it in a bit more detail a bit later. So you get probability S equals k times pi to the k, where pi is this expression we had earlier. So I can write it in this form, use this for PGF, so it's f of s evaluated at e to the minus lambda g z times mu I. Then if I set x to be 1 minus z in the equation here, you see that you get the equation for the extinction probability of a branching process with a Poisson offspring distribution with random mean lambda g mu I times s. So this equation will have either 0 or 1 or 2 solutions. Z equals 0 is always a solution. It's going to correspond to minor outbreaks. And if R0 is less than or equal to 1, then that's the only solution. If R0 is greater than 1, there's a unique second solution, Z hat, which gives the mean size of a major outbreak. Okay, so that's a heuristic argument to tell you what the mean size of a major outbreak is. This can be made fully rigorous using Paolo Scalia-Tomba's embedding method, which I'll just outline now. I won't give you all the details. Okay. Before I do that, sorry, I was run ahead slightly. Before I do that, I'll just explain how we get this random variable S here, which the limiting size of a local susceptibility set. Okay, remember I use script notation. Script S1 would be the actual set, local susceptibility set of individual 1, and Roman S1 would be the size of that susceptibility set. And I'll let A1n, script A1n, be the neighbours of this susceptibility set. So these are the neighbours of the individuals in the susceptibility set, but they they don't infect that individual, so they don't join the susceptibility set. And now I can form the network. I pair up the half edges when I do this configuration model at the same time as I construct this susceptibility set on a generation basis. And because all these things are being paired up uniformly at random, as n goes to infinity, you can use a coupling argument to show that S1, A1n converges almost surely as n goes to infinity to S and A, where S and A are the total progeny of a two-type branching process. Now, type 1 corresponds to people who join the susceptibility set, and type 2 are going to be these neighbours of the susceptibility set, the ones who are neighbours of individuals, but they don't actually, there's no local infection coming into them. So in this two-type branching process, only type 1 individuals have offspring. The total number of offspring of an individual is in the first generation is distributed according to this degree random variable D, and in subsequent generations it's according to this size bias D tilde minus 1. So that gives you all the neighbours of a given individual, but not all their neighbours are going to try and infect them. So you sample binomially the probability PL. PL is the local infection probability. And now these, in the forward process, I didn't say it at the time, it's more complicated because you've got, unless the infectious period is constant, the event you infect one neighbour or you infect another neighbour are dependent through the length of the infectious period. And so it's more complicated. It can be done, but it's a more complicated calculation. But in this backward process, this argument here, that's not the problem because people trying to join the susceptibility set are different individuals, and they are joining independently. So, so each birth here is type 1 independently of this probability PL, and as I say, only type 1 individuals give birth. And so this converges to this total progeny of this branching process, and going back to the previous slide, this gives you the equation for working out asymptotically the fraction infected by a large outbreak. Okay, so how can we try and make this rigorous? Well, we can construct the final outcome of this epidemic in a slightly different way. So I'm going to still use the directed graph of potential local contacts to model local infection, but I'm going to model global infection by giving each individual IID random variables L1 up to Ln. They're going to be exponential with rate lambda g, and you can view those as an individual's sort of tolerance to global infection. And it says how much global infection there is in the population before that individual succumbs to infection. And because all these infections occurring at points of Poisson processes, if I set these random variables to be exponentially distributed, then this model reduces, gives you the same final outcome as the one I had before. So I assume that each susceptible accumulates exposure to global infection at this rate here, and when individual i's total exposure to global infection reaches Li, that individual, it becomes globally infected. Okay, well, I'm going to just construct a slightly closely related model, but not quite the same. So I suppose that each individual now is exposed to, T here isn't time, it's just units of global infection pressure they're going to be exposed to. So I suppose that each individual is exposed to T units of global infection. Then I can let these critical exposures L1 up to Ln determine who is infected globally. Then I can use the graph of potential local contacts to then determine who is infected locally. And I set chi n of T to be indicator function that I is ultimately infected by this epidemic. So the whole population is exposed to just T units of global infection, then I work out who's infected subsequently, either globally from that or from the following on subsequent local infections. Okay, so this is this indicator function here, and it's 1 if its susceptibility set is contacted globally, and now that, if you look at, that's going to happen if the minimum of these tolerances over the susceptibility set is smaller than T. Otherwise, it won't be contact. This individual will not be infected by the epidemic. So the expected value of that is just given here, and it's just 1 minus f of sin evaluated e to the minus lambda g of T. And then I can sum up over Rn of T. If I sum up all these indicator functions, this gives me the size of this epidemic. And An of T, if I multiply the indicator function by the infectious period of individual I and sum those up, that gives me the total amount of infection or total severity in the course of that epidemic. Okay, I can now go back and relate this to the previous model. So I suppose now that you start by exposing each individual to T0 bar n, which is n minus 1 T naught n units of infection. So this could be just one initial infected you start with. T naught n would be the length of that initial infectious period. Okay, and then what happens is I expose the population to this amount of infection, then there's going to be more people who are going to be infected. Some will, from this global infection, they will create local epidemics, and that will create more severity. So I get T1 of, so I start off with here, this is this sort of function I had before, n minus 1 times An of T. So you start here, you get this much more sort of infectious pressure, so you go along to here, you go along to here, you go along to here, and this must stop after a finite number of steps. You've got a finite population. And when it stops, this gives you the final, up here, the final severity of the epidemic, and Rn of T, well, at that stopping point, it satisfies this equation here, T equals T naught bar then plus n to the minus 1 An of T. And the final size is just given by this R function evaluated at this stopping time, T infinity bar n, and the final severity is given by T naught bar n plus A n T infinity bar n. Okay, so what one does next is you prove a sort of a Granville type result for this function n to the minus 1 An of T, and that converges almost surely to some limiting function, which is not hard to work out, and then you get a central limit theorem. You get fluctuations about that limiting function, and so this boils down to a crossing T infinity bar n is a crossing point of a Gaussian process with a straight line. And then I'm not going to go through the details. I will say a bit more about how you work out the variance of this process, but you can, from that you can then get a central limit theorem for the final size of the epidemic. Okay, so let me just mention how we get the asymptotic mean and variance of this Gaussian process, or the mean and variance of the Gaussian process. So remember, Rn of t is just the number of people infected by this epidemic. This is the indicator function. Individual I is infected, so it's just n times that, which is n times 1 minus this generating function here. So as n goes to infinity, R of t, the mean is just that mean there, and we've already seen S1n goes to S, and so this converges to 1 minus f of s e to minus lambda g of t. What about the variance? So what we want to work out is the limiting variance of Rn of t. Rn of t, as I said earlier, is just the sum of these indicator functions. And now we can use the fact that these indicator functions, the model, they're exchangeable because of the way the model was set up. So, so this variance here will be just n times the variance of chi1n of t plus nn minus 1 times the covariance of chi1n of t and chi2n of t by exchangeability. This is just the variance of chi1n of t. Well, we've already worked out what happens to chi1n of t, so this gives you r of t, 1 minus r of t. So here, this limit we want is the same as the limit as n times the covariance. We've got n times the covariance of chi1n of t times chi2n of t, and we can write it in this form instead. Well, what's that? If you look at the covariance of these two indicator functions, so it's now the indicator function of individual 1 avoids infection, individual 2 avoids infection. So that's just the probability they both avoid infection minus the product of those probabilities. They both avoid infection if the union of the susceptibility sets of individual 1 and individual 2 are not contacted globally. So that's given by this expression here, and these are the ones we had before. And I can condition on the size of the first individual susceptibility set and the number of neighbours in that susceptibility set, and I can write it in this form here, where this is just a set, S of 2 minus 1 is just the size of the set difference between S2 and S1. Okay, so I want to work out that covariant, that function there. Now, if I condition on S1 of n, if I tell you how big S1 of n is, you can work out the probability that individual 2 belongs to into the first susceptibility set. That's just going to be S1 of n minus 1 upon n minus 1. And if that happens, there's nobody in individuals 2's susceptibility set that isn't in individuals 1's susceptibility set, so S2 minus 1 is just 0. And we know that that S1 of n goes to S as n goes to infinity. So this limit we want here, I can write it in this form here. So this is what happens when if 2 belongs to the susceptibility set, it happens with this probability. This is where this is coming from. You multiplying by n at the front, and you get that expression there. We've also got to work out what happens if 2 doesn't belong to the susceptibility set. Well, that happens with 1 minus that probability. The bit of 1 upon n disappears because the other bit's going to converge, and you end up wanting that limit there. Okay, to get that limit, generally it's difficult. It can be done, but I'm not going to go through the details. I'll just indicate what you do if the degree distribution is constant and the infectious period is also constant. It's a lot more complicated if we don't, particularly if we don't allow the degree distribution to be constant, but you can get an expression. So we construct the first susceptibility set as before, leaving the half edges corresponding to A1n loose, and now we construct this set, this S2n minus S1n on a generation basis, continuing to form the network as we go along. And if you do that, but if a half edge is paired with a loose half edge, there's no individual in S2n minus S1n. So if you pair up one of these A1 half edges here, you don't actually add to the susceptibility set. Well, if you do that, this process here converges to a branching process, which I call BP alpha n, in which each birth is aborted independently with this probability here. Because if you try to join up with one of these half edges here, you don't lead to a new individual. So this is the probability a birth is aborted. So if I let S alpha be the total progeny of that branching process, of this branching process here, then and psi of x comma alpha be the corresponding PGF, then if alpha is 0, you're back to the what we had before, S. And if you look at this thing we want to evaluate, then it turns. Ooh.
It's back.
Okay. It turns out it's you get sort of n times this expectation here, but just by the sort of the mean value theorem, you can evaluate this. It's this mean here times the derivative of this PGF with respect to alpha, and so you can work out what this limiting covariance is, and from that you can work out what the asymptotic variance of the epidemic is. Okay, just very quickly, one can use the same sorts of arguments to work out the variance of a giant component in a configuration model network. So if you let Rn be the size of the giant component, assume it's supercritical, then Rn upon n goes in probability to rho as n goes to infinity, where rho is given by this expression here, and z is the solution of this equation. So if you want to work out the variance of Rn, it's just the same as working out the variance of the people of the nodes which aren't in the giant component. So we want to work out the variance of Un. So n minus 1 times the variance of Rn is this, but asymptotically that's going to be the same as n minus 1 times the variance of Un tilde, where Un tilde is going to be the number of vertices in components of size less than n to the beta. Where you take any beta less than 1, because the second largest component has size log n. And now you can do the same sort of arguments. You want to work out how many individuals are in components of size less than n to the beta, and rather than having susceptibility sets, you have these components, and you can do similar sorts of things that I've described before, and you can use that to work out the asymptotic variance of the configuration model giant component. And if you do that, you get a different answer depending whether you use a mono-read random graph or a Newman-Strogatz-Watts random graph. So in the former, the degree sequence is deterministic, and the second one you have IID degrees, and the second one, although the mean size of the giant component is the same in these two models, when you look at the variance is larger in the second one, because you've got some randomness in the degree sequence which feeds through into the variance to the size of the giant component. Okay, so you get these formulae fairly, well, I don't know if they're simple or not, but they're fairly, once you've worked out what Z is, they're fairly simple to calculate at least. Okay, I'm just going to run out of time, so I'll go through this fairly quickly. So here's some simulations of the model I've been describing. So here, locally it's below threshold, but above threshold overall. Here it's above threshold, and here you've got no global contacts. And these are just sort of some calculations of the mean size of the epidemic and also of the variance based on 10,000 simulations. And the theory I've described doesn't actually cover this case. We just let lambda g tend to naught in the formulae, and it seems to be giving good answers, but we haven't got a proof yet that gives you the right answer. But generally, the asymptotics seem to be working pretty well. Certainly once you get to 1,000, they're working well. I think I'll skip these through lack of time. So here we look at the effect of, so we've got two degree distributions, each I think have mean 8. The solid lines are the ones with global contacts, and the dashed lines are the models without global contacts. And the red ones, you've got a scale 3 distribution, degree distribution, and the blue ones are constant. And I'll just make 2 points. The effect of these global contacts, so the effects is, you just want to look at the difference, vertical difference between these lines, is greater for the constant degree distribution generally than it is for a scale 3 degree distribution. And it can be quite significant. So if you look at the constant degree distribution, if PL is set at 0.1, if you haven't got global contacts, then it's subcritical, but if you have global contacts of this, I mean, there's quite a few of them, about half the population is infected. Okay, well, that's not really a fair comparison, because all we're doing is just adding in these global contacts, and we're not making any adjustment. You're bound to see a larger outbreak. So this is something done with Ben Davis, a student of Dave and mine. So what we've done here is we've fixed R0 to be 2, and we vary lambda g from 0 to 2, and choose the local infection probability so that R0 is maintained at 2, and plot how the mean size of the epidemic changes as you change the model from homogeneously mixing to one which is a standard network model. So I don't know if this relates to what Tom was saying yesterday, but with a standard network model, you can get any Z. Almost, for a given R0, you can actually get almost any Z, and you probably can get any Z you like. So even a homogeneously mixing model, you get a fraction of 80% of the population is infected. As you start putting these heterogeneities in, here heterogeneity is just due to the network, then it can have a big difference on the size of a large outbreak, even though you keep R0 fixed. At this end, it's easy to work out what happens. Essentially, if there's if the variance is larger than the mean, then as you add the heterogeneity in, you decrease the size of a large outbreak, and if it's smaller than the mean, you increase the size of a large outbreak. But these graphs need not be monotonic. They are here, but you can put an example where it's not monotonic. Okay, I now want to change tracks and say a bit about this model for clusters and tuning clustering and degree correlation. So, okay, there's lots of models of random networks that include clustering and degree correlation. What I want to do here is to present a model which allows a wide range of tunable degree distribution, clustering and degree correlation, but also allows theoretical analysis of epidemics on the network. And we're going to do this we're going to introduce clustering by sort of putting households or cliques into the model. So in real human epidemics, households are a very important feature of epidemic spread. But here, I'm just going to use them as a device to introduce clustering. And so I'm going to have households, and then I'm going to, each household is going to be a complete graph, and then, so you've got these local edges within households, and I'm going to have these global edges between individuals in distinct households. And the way we pair up these, which I'll explain shortly, these global edges is going to attune the degree correlation. So we'll have, notation slightly different. We've got little n nodes, label them 1 up to n. First of all, we form the local edges. So I take IID samples from this household size distribution H. I put the first H1 nodes into group 1, and then local group 1, the next H1 up to H2 into plus 1 up to into local group 2, and so on. So I can use these random variables to partition the individuals into cliques. And all nodes in the same household are connected to each other to form a clique, and the local degree of a node would be just one less than its household size. To form global edges, so what we do is we take G1 up to Gn or IID according to some global degree distribution, and it's going to be some modification of the configuration model, so we attach GI global stubs to node I. Then I'm going to attach X labels, I'll say what these are in a second, in IID labels to each node. These are going to be Bernoulli trials. It's either going to be a 1 or a 0. R is going to be a parameter which is going to tune the degree correlation. So they're binomial with Bernoulli with success probability mod R. And so I'm going to have to each of these stubs there's going to be some are going to have label 0 and some will have label 1. The stubs which have label 0 I'm going to pair up uniformly at random like in a configuration model. So I'm left with a load of stubs which have label 1. The ones which have label 1 I separate them into I look at their total degrees of those stubs. So it's going to be the local degree plus the global degree. And I'm going to use that, I'm going to separate them out into NQ equally sized quantiles. And then it depends whether R is positive or negative. If R is positive, then for these ones with label 1, I pair them up uniformly at random within their quantile. And if R is negative, we pair them up with the opposite quantile. So if R is negative, then somebody from the first quantile, the stub will be paired up with somebody with stub from the last quantile, and so on. So the former will induce positive correlation between the nodes because they're being paired up with stubs of roughly the same degree, and the latter will induce sort of negative, make the correlation more negative because there's going to be some positive correlation because they're in the same household. Okay, so it's fairly straightforward to work out the properties of this model. The degree distribution, well, the degree of an individual is just given by its global degree plus 1 minus its size by its household degree, okay, because an individual is more likely to reside in a larger household than a smaller one. The clustering coefficient is fairly easy to work out because when n is large, because the way these global stubs are paired up, you only get triangles within households, so it's fairly straightforward to work out, count up how many fractional triangles there are out of all triples, and you get an expression that looks like this. Degree correlation, it looks pretty ugly, but it's fairly straightforward to work out. You just so you want the correlation between of the degrees of the ends of a randomly chosen node. You just condition on whether this edge. You just condition whether this edge is a household edge or a global edge, and then you can do the calculations. So if it's a household edge, then you get positive degree correlation because they're coming in because you know the household degrees are the same of the individuals at the two ends of the node. If it's a global edge, then the degree correlation is coming in deduced by how you paired up these global stubs. Okay, so if you take a Poisson degree distribution, for example, so if G is Poisson with parameter gamma minus mu, and H is called Poisson plus, so it's the Poisson distribution conditioned on being positive with parameter mu, then the degree distribution is Poisson with parameter gamma, and you can work out what the clustering and degree correlation is. And I'm not going to go through the details here, we'll run out of time. So you can construct a picture which looks roughly like this. So along here I've got the clustering coefficient. Up here I've got the degree correlation. Here, this sign 1 here is when you've only got 2 quantiles, and anywhere in this region here you can tune your models to have a clustering coefficient and a corresponding degree correlation. And as you allow you have more quantiles, you get a slightly bigger range of models which are covered. I mean, in one sense it's deceptive because it looks like if you get to 10 you're very close to NQ is infinity. That's the case where you essentially you pair up globally with somebody of the same degree, or if you've got positive correlation, R is positive, otherwise you pair up with somebody of the opposite degree. And although the models look close in this picture, in fact the epidemics on those models behave somewhat differently. Okay, so the epidemic we have is an SIR epidemic, similar to before, but except now we've only got one infection rate, the lambda down an edge. And here's some simulations, and it's down here is sort of qualitatively you get a similar sort of picture. So now it's not so clear when you've got sort of 300. The distinction between major and minor outbreaks is not so clear, and here it's not very clear at all. But as you increase the population size, it becomes clearer, and if I was to make it bigger, it will become even clearer. So what we do is we approximate the early spread of the epidemic by a branching process as before, but now it's going to be a branching process of infected households. So if the epidemic starts over here with this individual here, there'd be some local epidemic within the household, and then there'd be a global spread to another household, and so on. Early on in the epidemic, the way the graph is formed, pairing up the global edges, you're unlikely to pair up with a household which has previously been infected, so you can approximate the spread by now a multi-type branching process. It's a spread of infected households, and it's multi-type because you need to keep track of the quantile that's stubbed. So here, for example, you need to know what quantile this stub belonged to, which formed this edge, to be able to work out how many people, how many edges there are coming out from this person here in the graph. So it's a multi-type branching process. And you can use similar methods. You just work out the threshold parameter now is it's the largest eigenvalue of the mean matrix of that multi-type branching process, and you can work out the probability of a large outbreak. And you can do a similar thing for the size of a large outbreak, at least informally. You construct a susceptibility set now on a household basis. We haven't got global contacts here, so now the interpretation is that if you construct this susceptibility set, so all these blue individuals of this red individual susceptibility set, if initially infected with amongst any of these blue individuals, then the red individual will be ultimately infected. And what one can show, well, for a slightly simpler model than this, this susceptibility set can be approximated by a branching process. And if that branching process doesn't go extinct, then this individual will be infected by a large outbreak with probability tending to 1 as n goes to infinity. And so you can work out the asymptotic size of a large outbreak. I think I'll skip the simulations and just give a couple of graphs. So here we have a model. We've got a +1 degree distribution. Got 10 quantiles, and what we're doing is we as R ranges from -1 to +1, you're increasing the degree correlation, and so we plot here the degrees. The infectious period is constant, so the probability of a large outbreak is the same in that case as the mean size of a large outbreak. and we plot this for various choices of this infection parameter, see how the size of a large outbreak depends on the degree the correlation, or this parameter R, which controls degree correlation for different choices of clustering. And what one can see here is that if the model is well above threshold, up here say, then the degree correlation is having little effect on the final outcome. But the effect it does have, it tends to make it smaller. But if the epidemic down here is just supercritical, then the degree correlation is having a larger effect, and it's going the opposite direction. It's tending, as you increase degree correlation, the epidemics become larger. And if you look at this situation down here in more detail, you get a picture that looks like this. So there's not very much clustering here, but as we increase R, you get this sort of monotonic behavior, where initially it decreases, then it increases, and then it decreases again, and you get a situation here where it's sort of subcritical in this range. So you get a rather strange behavior of the final size with degree correlation. So one final picture. So what we've done here, so we take up the model we had before. This is the picture showing the range of possible pairs of clustering and degree correlation allowable. So if we start off here, then I can reduce the clustering to 0 by just going along the models you get as you go down that red line there. If I do that and work out the size of the epidemic, it's what I call unrewired, you get this blue curve here. Alternatively, I can start with this model and I can break up some of the households. So I break up a fraction of the households with some probability, say probability P. When I break a household up, I just break all the edges in that household and make them into stubs, but I label those stubs with the household size. And then I pair up all stubs of the same household size uniformly at random. And so by doing that, I'm getting rid of some triangles, so I'm reducing the clustering by a fraction P. And if I do that, I get as I change P from 0 up to 1, I can also get a sequence of models which have the same clustering coefficient degree correlation as I had before, because the way we break them up and pair them together, you're not changing the degree correlation. If I do that, and I get this graph here. So in both of those models, as you increase the clustering, you decrease the spread of disease, but it's different for the two models, even though they have the same values for C and degree correlation rho. Okay, just a few brief concluding comments. The asymptotic approximations are good for ones that generally for moderately sized populations. All these things we've been looking at can each have a significant impact on disease dynamics and hence on various control strategies you might put in place. As you increase the clustering coefficient, you tend to decrease the spread of disease. The effective degree correlation is much greater when the disease is well above threshold, close to threshold when it is well above threshold. But as I've just shown, there's distinct models having the same parameters but different epidemic properties, and so one has to be very cautious if one wants to try and extrapolate these conclusions to real-life networks. Okay, thank you very much.
So are there questions for Frank? Could you repeat your assumptions on the infectious period? So do you allow for a completely general distribution?
Yeah, you need to know what it is, but
it can be anything.
It can be anything, yes.
So I thought it was much harder to analyze epidemics with non-exponential infectious periods. So it's a general epidemic on the configuration model with a general infectious period.
Yeah.
That's done.
Well, it depends what you mean by done, but
that's rigorously analyzed.
yes. Well, most aspects of it are rigorously analysed. I think the central limit theorem for the final size, that wasn't actually covered. If you take a configuration model epidemic, that's what you get by letting the global lambda g tend to 0.
Yes.
I'm not sure that's been rigorously proved, that central limit theorem, because I mean here it's just heuristic. I think everything else is done in the general case.
So if you can do the configuration model, I think of the configuration model as a particular graphon model where the graphon is rank 1. So do you think you could do a general graphon model which are rank 1 graphons?
I'm not really very familiar with graphons, so...
So I would just generate a network by saying the following: I have some function, so I have some feature space, think of it as the interval 0, 1,
yeah.
and a probability distribution on it, think of it as a uniform distribution, and then I have some function f of x, which indicates sort of how, it's sort of like a degree distribution of this x. And now I connect, and so now I have n vertices, I have x1 up to xn,
Yeah.
which chosen uniformly at random. And now I connect I and j with probability f of xi times f of xj.
Well,
So this is very similar to the configuration model where you would just say I fix a degree sequence and then connect with probability proportional to the degree of I and the degree of j.
We should discuss offline.
yeah, well, I think Peter Neal has done some work which I think does that for certain choices of this function. So I think if it's the product x times y upon, what is it? W1, if you've got these weights, it's like a weighted, you put weights at the nodes, and if you...
Right.
So W of x and y would be like just a product function.
Yeah, if it's a product function, then if it's you can show, I think, that the final, if it's appropriately chosen, the final outcome of an epidemic on that configuration model is the same as another epidemic model for which you can work out the central limit theorem, etc. And so you would get results for example, the large component, giant component on that model.
And what about stochastic block models? Could we redo what you did here for stochastic block models?
Well, so Dave and Peter Chapman and I have been doing some work on that for whilst we've been here, actually. Not actually the stochastic block, well, something closely related to the stochastic block model. Then you can get quite interesting, well, it depends how you control what sort of how strong the links are between different individuals and different blocks. Mm-hmm. So if the infection, in our terminology, if it's
if it's greater inside the block than between the blocks.
It's amount of difference. I mean, if it's of the same order, then you get quantitatively the same results in a stochastic block model. Mm-hmm. But if you scale it differently, so you get in very few infections, but some between blocks, then you get a sort of a random outcome where there's going to be a mixture of sizes of epidemics, and so we've been doing some work on that.
That's what I was trying to get to, because you now might be able to study how sort of infections may stay within a certain group or not.
Yeah. So you get much more interesting.
So there's some scaling with n such that they tend to stay inside versus tend to spread across.
Yeah, essentially.
And if the scaling with n is the same, then you just get
you get the normal thing. If it's
the
different,
normal giant component.
Yeah. But if it's different, then you get you don't get a deterministic size for the giant component, for example, because if it's scaled differently.
Sure.
Are there other questions? If not, we thank Frank again. And there is coffee.